Okay, so here we're going to wrap up this section on linear independence and focus on a couple of just kind of results here that to extend kind of connections here with some topics that we covered before, right? And first one being a non-singular matrix. All right, now recall that a non-singular matrix dealt with a square matrix. Right, so if A was non-singular, it was square, right, and all of its columns were linearly independent, right, and that meant that, a couple different things you can interpret this, right. The null space was the zero vector only the trivial solution, right. But now that we have this definition of linear independence and connecting a set of vectors in terms of having those be the vectors, the columns in a matrix, and determining whether it is linearly independent is like solving the linear system like this, right? Where this matrix A, right, is made up of the vectors that we are aiming to determine if they are linearly independent or not. Right? So as it turns out here, right, when we're looking at square matrices, right? In other words, when the number of rows is equal to the number of columns, right? We have a nice little result here. Looking here in our book, we have theorem NMLIC, right? So this says non-singular matrices have linearly independent columns. So it says suppose that A is a square matrix, then A is non-singular if and only if. Right, so again, strong connection here. If and only if A form a linearly independent set, right? Now that makes total sense, right? If we think of the columns of this matrix to be a linear dependence relation, right? Set equal to the zero vector, right? Well, if it's non-singular, right? The only solution that's going to work is the trivial solution, right? So we can now have another form to describe, right, non-singular matrices now in terms of linearly independent sets. All right, so let's take a look here at this theorem NME2. In a previous section, we made a connection between these four different properties, which we said they were equivalent, right? And again, when I say that these are equivalent, I mean if one is true, if I know one is true, then the other follow. Right, so previously we took a look at those first four conditions, or those first four properties, where A is non-singular. A row reduces to the identity matrix. The null space of A contains only the zero vector. The linear system has a unique solution for every possible choice of B. All right, so that was previously when we were discussing non-singular matrices. Now we can add this fifth statement here. The columns of A form a linearly independent set, right? And that's just a result of the nature of how we are formulating these matrices A and the vector sets that we are studying here, right? So now we can add to this NME2, and this won't be the last time we add to this, right? As we can see, right, there's a lot of structure kind of being built here where we can describe different things, right, in different mathematical objects here that aren't necessarily all tied back to our linear systems of equations. Okay? All right. So now let's take a look at, so we have talked about non-singular matrices. Now let's go back here to talking about another result here. It has to do with null spaces. All right. So again, a null space, the null space of a matrix. Oops. Excuse me here. All right, here, let's see here. Give me 1 minute here. Okay. All right, so we defined previously the null space of a matrix. Right, again, very similar, just a solution. Here we just kind of generalize, it doesn't have to be a square matrix, right? So we can interpret the null space as just the solutions of the homogeneous system, right? And now we can bring into this idea, this notion of linear independence, right, to a null space of a matrix. So first let's introduce, let's say we had this matrix, 9, 9, 0, 2, 0, 1, 3, 5, negative 4, 12, 12, negative 1, and 1, negative 3, 5. Okay. All right. And I want to determine the null space. Right now, I interpret this as just the coefficient matrix, right? Again, usually when dealing with homogeneous systems or really just a matrix, right? We're not really tying it to a linear system, right? Then I don't think of it as an augmented matrix, just a coefficient matrix, or in general, just a matrix. And when we say a null space, we look at, right, if we were to think of this in terms of a homogeneous system. All right, so kind of our last result here in this section is this idea of a basis. So here, let me bring back here. We're going to take a look at theorem basis for a null space. All right, now let's read the theorem here, and then we'll kind of try to parse through it and illustrate it with the an example with a matrix that I had in the on the virtual blackboard there. Suppose that A is an n by n matrix and B is a row equivalent matrix in reduced row echelon form with R pivot columns. Let D be the set of the pivot columns or the column numbers of the pivots, and F be F1 through Fn minus R, right? Stuff we've covered before. Okay, be the sets of column indices where B does and does not respectively have pivot columns. And we construct the n minus r vectors in this certain way. All right, so again, where the notation here, really, I'll go through what all this means, right? Where it's 1 when it's the free variable, and then solving for the dependent variables in terms of what's in the other columns. Right, so we define the set in this manner: z1, z2, z sub n minus r. Right, so however many number of free variables we have, that's how many vectors we're going to have. Right, so we can define the null space as a span of this set. Okay, so not only that, this set S is linearly independent. Okay, so now let's parse through what this means, right? So going back here. All right, so let's say here I reduce row echelon form this matrix. So here we reduced row echelon form. We have 1, 0, 0, 31 over 27, 2/9. And here we have 0, 1, 0, 1/3, and negative or 1. This is a 9. And then 0, 1, 0, 0, 1, 1/3. And negative 1. Okay, and we could see here, these are our pivots. All right, so our alpha 1, alpha 2, alpha 3. All right, and then here these are going to be our free variables. All right, alpha 3, alpha 4, alpha 5. Okay, now here we can start by, here we'll say alpha 3 is equal to S, alpha 4 is equal to T, right? Some kind of parameter here. Okay, and we'll just call this matrix A to keep with the same notation as our theorem here. All right, so with that in mind here, then we can go ahead and solve through, oh, excuse me, I have my indices wrong here. So we'll call this alpha 4 and alpha 5. All right, again, as we think of these as the columns as vectors here. So then solving for alpha 3, so we get alpha 3 plus 1/3 alpha 4, which is S, minus 1 T equals to 0. And then we get alpha 3 to be equal to negative 1/3 S plus T. All right, and in a similar way, we get alpha 2 is equal to negative 1/3 S minus T. And alpha 1 to be negative 31 over 27 S minus 2/9 T. So this formulation is what that theorem is getting at here. Right? And actually, before I jump back to the theorem here, let's write it in our vector notation here. So the vectors here would be S minus 2/9 T, negative 1/3 S, minus T, and then negative 1/3 S plus T, and then we got S and T. Which I can write as S negative 31 over 27, negative 1/3, negative 1/3, 1, 0. Okay, and then plus T, negative 2/9, negative 1, 1, 0, 1. Into its components here. So here, that's what all this in our textbook, what this statement is telling me, right? Z, J, sub I, right? Those are just elements. It's 1, right? When we're dealing with a free variable, right? As you see in the previous one, and it's negative, or the opposite of what is in our reduced row echelon form matrix, right? So here, as we see here, right? 1, right? Were the free variables, and then the opposite. So you see here of what's in our reduced row echelon, right? So that's all that notation is, right? But again, here, focus more on how do we arrive at that, the process and working our way to this statement here, right? Now, to describe the null space, previously we described writing it as a linear combination in a set notation, and then call this S and T, let S and T be any real numbers. But now what we can do here is we can write it as a span. We could say, all right, well, the null space is just a span, set S and T equal to 1. And we could write it like that, right? Because again, what's a span but the set of all linear combinations, right? And that's what we have here, right? This is a linear combination, and this is the set of all of them, right? Not only that, right? What that theorem tells me is I can use this notation, the span notation, but now this is guaranteed, to be linearly independent. All right, so I don't even have to check it. That theorem tells me that if you find a null space here, right, those vectors are linearly independent, right, by that theorem. Right, that's a property of the process here.